All right, in section 3.5, we are looking at limits at infinity. So let's start with a little bit of definition of what that means. So we're going to let L be a real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists a m greater than 0, such that f of x minus L is less than epsilon whenever x is greater than m. And all of this should feel like, I feel like I've seen something like that before, right? You have. We have the corresponding statement number 2 for a value being a low number. So m is a big number, n is a big negative number is really what it is. That's why they're using a capital. It's a large number, but it's negative. So the statement, the limit as x goes to negative infinity of f of x equals L, means that for each epsilon greater than 0, there exists an n that's small, it's negative, such that f of x minus L is less than epsilon whenever x is less than n. So I don't have a lot of space on this screen, but I'm going to draw a curve that you're very familiar with. The curve I'm going to draw is 1 over x. And you know basically what it looks like. It has this kind of a shape. I'll do it in red just so it's different from the black. Looks like that. I think I flipped it upside down. My bad. So sorry. How about like this? There we go. Both of those graphs will work for what I'm doing, but this is the graph of 1 over x. Here's what this is saying. If I go out here far enough to m, or go over here far enough to n, that this, if there's a limit here, which there is, they get really tight. The distance between these is going to 0. That's what epsilon is meaning for us. Every time we see epsilon, it's talking about something getting infinitely small, right? This space is compacting, and if I go out far enough, it will compact really far. And if I go out further, it gets even closer. That's what a limit is, right? It's what it's tending toward, or what it's getting really close to. And in these cases, it is really getting really close to it. It doesn't equal it, because I can't equal infinity for x anyway, right? X can't equal infinity. That's not a thing. Infinity is a concept of how close you're getting to something. It's not a value. It's not 5, right? It's not 150,000. It's infinity. So what we're looking at here is things where we have getting infinitely close to a specific value. And that should feel like something you've seen in algebra. It's something called a horizontal asymptote. So the line y equal L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of the function is equal to L, or the limit as x approaches positive infinity of your function is equal to L. And the graph that I just drew, which let me just copy it over here, and we'll put it back. I didn't mean to do that, but that's fine. Okay, here's my graph. What's the horizontal asymptote of this graph? Okay, what's equal to 0? Y. Yeah, the horizontal asymptote is at y equal to 0. So we have a tendency to recognize the value as the number, right? The number is 0, or sometimes we'll have a number as 3 or something like that. But this is a y value, right? It's the horizontal line, and horizontal lines are y equals. So I'll do it we'll do blue. It's this line, right? Can you see that dotted blue line overlaying my black? That's the one we're talking about. That's a y equals line. So a horizontal asymptote is y equals 0. Now, what you probably remember from, or at least you will remember shortly after I say, like, oh yeah, it sounds familiar, from algebra, is that you can kind of look at the equation and figure that out, right? Now, it's not the denominator equaling 0. That's where we get vertical asymptotes, right? So pause on that real quick. We already talked about those things. It has to do with whether or not the denominator has a bigger exponent than the numerator or not, right? So when the exponent on top is smaller, certain things happen. And when the exponent on bottom is smaller, certain things happen. And when the exponents are equal, certain things happen. And that's what you look at in an algebra course for making that decision. So our limits, however, so if we have R is a positive rational number and C is any real number, if we have functions that look a lot like the one I just did, 1 over x, but more generally, any constant over any power of x, right? This is a generalized form for the example that I just gave. As x goes to infinity, the limit's 0. Furthermore, if x to the r is defined when x is negative, right, then the limit as x goes to negative infinity is actually also 0. So that's what this graph is saying. The limit on the right-hand side, the limit on the right-hand side, the limit on the left-hand side, they're both 0. And this has that form. I have a constant over x to some power. It's just a not exciting value, right? X to the power of 1. All right, so looking at these examples, we're going to go through using that process for the moment, and we'll talk about some of the other things that we have seen in a little bit too, or at least how they're related to what we're seeing now. All right, so taking a look at this, right now we have h of x is equal to this f of x function, which is what we have at the top, 5x cubed minus 3x squared plus 10x over x squared. And so we're going to actually push these functions together. It's a composite function. We're just going to compose them. So how about we use the right tool. So I have 5x cubed minus 3x squared plus 10x. And it's all over x squared. Is that part okay? Just a composite of functions so far. So what we're about to do next is something you've seen us do before. We've done it when we did derivatives. We can't use this theorem yet because this theorem has a constant on top, right? And our equation does not have a constant on top. It has a polynomial on top. We want to change this equation into something that has a constant on top. So how do we do that? Well, the way that we do that is we divide each piece by x squared. We're just separating all the pieces out. So we can rewrite this as 5x cubed over x squared minus 3x squared over x squared plus 10x over x squared. Does that make sense? We have done this before for the purpose of finding derivatives. It's not the only way to find this particular one if you were trying to do the derivative, but we've done this process. Some of these simplify really nicely. What's the first one become? 5x. 5x. What's the second one become?
3.
Yep, negative 3, because there's a negative in front. And then the last one simplifies some. It becomes 10 over x. Okay, so the first thing to do when we're working with these limits is to first figure out what's the function we're talking about. And how do I reduce it or simplify it, make it easier to work with, okay? So that's what we've done so far. We haven't found any limits. All we've done is to just figure out what our function actually is in a more condensed form, more user-friendly form. What we want then is we want to find the limit as x goes to infinity, it says, of h of x. So that means now I'm going to do the limit as x goes to infinity of 5x minus 3, whoops, too soon, plus 10 over x. And we've had properties of limits to know what we do with this. So we take the limit of each individual piece. So it looks like this next. This is the limit as x goes to infinity of 5x plus, or minus if you will, the limit as x goes to infinity of 3 plus the limit as x goes to infinity of 10 over x. What is the limit as x goes to infinity of 5x? It's not 0. One of these is going to be 0, but it's not this one.
It just gets it to
It gets infinitely larger. Okay, so one way to think about that is a graph. What does the graph of 5x look like? Well, it looks something like this, right? As x goes to infinity, as we go infinitely to the right, the y value goes to infinity. That's a graphical standpoint. From a numerical standpoint, you can talk about what happens if I plug in bigger and bigger and bigger numbers for x, right? What if x is 100? What if x is 200? What if x is 300? What happens? It gets infinitely big, right? So you can think about it from a numerical perspective as well. So this first piece is actually infinity. The second one we've talked about the limit of a function like this, 3. What's the limit if you have a constant of a function, no matter what x is approaching? 0. Nope. That's the derivative. Nope.
15.
It would be 3. Thank you, Elijah. It's not 15, no. It's 3. So let's think about it from a graphical standpoint. From a graph. So you can use lots of different tools that you guys have available to you from a graph. What does the line 3 look like? Well, it's y equal 3. It looks like this. What's the limit of this graph as x gets infinitely large?
It's always going to be 3.
It's always going to be 3. And that's why it doesn't matter that x is going to infinity here. X can be going to anything for a constant function. And it's always going to be 3 because 3 is constant. You can also think about it from a numerical perspective. If I put in x is equal to 10, what does this equation, right, y equal 3 look like? Well, it looks like 3. If I put in x is equal to 100, what does the equation look like? 3. Y equals 3. It's always y equals 3 because it's a constant. So that's pieces 3. All right, which must mean that the last one is 0, because I mentioned one of them was. So let's see why it's 0. Why should this one, the limit as x approaches infinity of 10 over x, be 0? Why should that work? I mean, we can talk graphical, we can talk numerical, but we actually have another tool as well.
The rules we just talked about.
Yeah, the properties we just talked about, in particular this theorem, right? This theorem says if I have a constant, which I do, 10, over x to some power, which I do, it's x to the 1, then as x goes to infinity, this limit's going to be 0. So we actually get that 0 down here. So if you're doing your problems on your test or a quiz or something like that, I would expect to see those 3 pieces that you've identified what they each are individually. But then you have to make amends for that, right? What is infinity minus 3 plus 0?
Just infinity.
It's infinity. So this is infinity, but we're going to break down the individual pieces along the way. Does that make sense? Okay, so we're going to change the numerators, what we're going to do for part B. I'm sorry, the denominator. I meant to say the denominator for part B. So the numerator is still the same f of x that we had before, 5x cubed minus 3x squared plus 10x. The denominator now is not x squared, it's x cubed. Process is the same. So I'd like for you to write down the f of x into location, like put it where it's supposed to go, and reduce it like we did. So do the same thing we did to the last problem. I'm going to have you do it first, and then I'll write down what I have. We'll make sure that everybody's on the same page. Does your first step look like this? Does it look okay? All right. Now, whether you write them separated or whether you jump over that step, right? So if you need to write it like this first, you certainly can. If you are able to go from here to here, that's just fine too. What did you get for the last step, the one that looks like this on this one?
5 minus 3x plus 10 over x squared, or 3 over x.
Okay. And then what?
Plus 10 over x squared.
Okay. Do you agree with Josh? Looks good? Okay, so we're all good so far. Okay, the reducing and getting it cleaned up is important because otherwise we're not going to be able to proceed with finding the right answer, right? So it's important that we've got that. Cool. Now we're going to take the limit as x goes to infinity, of, and I'll just put the function itself that we have now in here instead of writing the h of x part. It's 5 minus 3 over x plus 10 over x squared. Okay, that's what we're finding. This is what we've been asked to find, right? And from here, we're going to write out individually each of the three pieces. I expect to see that. All right, that is a property of limits that we learned a long time ago. Feels like forever ago anyway at this point. Way back at the beginning of February. So we have the limit as x goes to infinity of 5 minus the limit as x goes to infinity of 3 over x plus the limit as x goes to infinity of 10 over x squared. Individual three pieces. What's the limit of 5? 5. Constants are the favorite. I mean, they really should be. Anytime you see a constant, you should think super easy stuff. It's just that number. What about the second one? What's the limit as x goes to infinity of 3 over x? That's 0. So technically I have minus 0 here because there's a negative. It's not going to affect anything, but there is a subtraction sign from that. How about the last one? 10 over x squared limit. Also 0. So I now have 5 minus 0 plus 0. My limit is actually 5. And while I don't have a third problem like this, I want to show you just real quick so you can see that if the problem had just a slightly bigger denominator's exponent, the answer would change yet again. Okay, so over here when I divided by x squared, I got an infinite limit. Here when I divide by x cubed, I get a constant 5, right? If I did the same thing, so I'm not going to write all the details out, but if I did the same thing, was it cubed? Yeah. And I divided by x to the 4th, and I reduced this, I would end up with 5 over x, 3 over x cubed, and 10 over x squared. I'm sorry, 3 over x squared, and 10 over x cubed, right? That's what it would be if it was x to the 4th. What would each one of these limits be?
0.
They'd all be 0, right? So the power in the denominator compared to the power in the numerator matters. And what you might remember, and if you don't, it's okay, but what you might remember and feel like this sort of looks like something I've seen before is when you talk in college algebra about how to find horizontal asymptotes specifically, what we do is we look at the exponents and we say, if the exponent, is this the first one? Yeah. If the exponent on top is bigger, there's no horizontal asymptote. If it's 1 bigger, which this one is, we could get something called a slant or an oblique asymptote. Do y'all remember those? We'll talk more about these in section 3.3 when we come back after Easter. But there's no horizontal asymptote. Well, if there's no horizontal asymptote, that's why I get infinity. Or it could have been a negative infinity. Like that would have been an option too, depending on the functions that I'm working with, okay? So if the numerator has a bigger exponent, I don't have a horizontal asymptote. If the exponents are the same, that's what happens in part B as it was given, right? I have x cubed on top and an x squared on bottom. Then what I do is I use the coefficient of the x cubes, because that's the biggest exponent. Well, what's the coefficient of 5x cubed? 5. What's the coefficient of x cubed on bottom? 1. And what's 5 over 1? 5. And we sure enough get the limit is 5. And then the last one that I just sort of threw in here talks about what happens when the numerator on the bottom is, not numerator, the exponent on the bottom is bigger, right? On this one, I have an exponent of 3 on top and an exponent of 4 on the bottom. When the exponent's bigger on bottom, I get 0. And it always works that way. Those are the only 3 options when we're dealing with polynomial functions embedded inside of the rational function form, okay? So it's going to mirror what you've seen before, but you're doing it from the perspective of limits, from a calculus standpoint, okay? All right, let's take a look at what's left. The first three, because I threw that one in there, that we did, all had a single x squared on bottom, right? Or x cubed on bottom. What's different about this one?
It's a lot more than just x
it's a lot more than just x cubed on bottom, right? I have pieces on bottom that are not singular kinds of pieces. And that makes things a little bit messier. It doesn't fit into the nice box of things that we were just doing. So I'm going to have to use a different technique to do the process. Okay, everybody okay with that so far? This will not work the same way the one did before. It doesn't do the same thing. So what do we do? Well, again, from the standpoint of algebra, you should be able to look at this and say, what's the numerator's exponent? What is it? It's just 1. Good. What's the denominator's exponent? 3. So the denominator's exponent's bigger. This limit should be 0. And it will be. It will be. But we're going to do it from a calculus standpoint. Right? We're going to look at this from the standpoint of limits and why that works. So I know sometimes it feels frustrating when you move into a different topic of mathematics and you're like, I already knew how to do it that one way before. Why do I need to know how to? It should validate it for you. It should be telling you all of math is connected and it makes sense. This new way that I'm thinking about it with limits, which will allow me to do more things than just rational functions, still works for the same things that I did before. Okay? That's what it should be feeling like to you, is that things are making sense the way they should. So here's how we do this. We actually take a look at what is the biggest exponent, which we already said was x to the third, right? The cubed is the biggest exponent. And what we're going to do is we're going to multiply on the top by 1 over x cubed and on the bottom by 1 over x cubed. Okay, so it's okay that that doesn't sort of make any sense right now. You'll see why we're doing it in a second, but just that's what we do. Biggest exponent, we multiply by 1 over it. Okay? So far, so good? Okay, and then we're going to distribute to each of the pieces that we have. Now, as we do this, we rewrite limit, just like we have seen before. This is the limit as x goes to infinity until I actually considered the infinite values. I keep rewriting that piece. So if I distribute the 1 over x cubed through, the first one is 3 over x cubed. What happens when I multiply 2x by 1 over x cubed? 2 over x squared. Perfect. On bottom, 3x cubed over x cubed.
Just 3.
Just 3. And the last one I have 1 times 1 over x cubed. So it's just 1 over x cubed. Okay, each of these pieces can use that theorem. Right? All 4 of those pieces are now in the form that matches this. They're all a constant over the cubed or the squared or the whatever, except the one that's a constant itself. Agreed, which is probably why Josh is looking at me funny. Like, wait a minute now. And you're right, the constant part is not. But we know what to do with the constant part. But all the other pieces fit in with that theorem. So we're going to do the same thing that we did when we got them separated out, right? When I separated this piece out so that says 5 minus 3x, or 3 over x plus 10 over x squared, I actually separated the limits out. So I'm going to have the limit as x goes to infinity of 3 over x cubed minus the limit as x goes to infinity of 2 over x squared divided by the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 1 over x cubed. That's what I have, all of those pieces and so forth. Well, what is the limit as x goes to infinity of 3 over x cubed? It's 0. What is the limit as x goes to infinity of 2 over x squared? 0. What is the limit as x goes to infinity of 3? 3. And the limit as x goes to infinity of 1 over x cubed? 0. We have 0 on top. We do not have 0 on bottom. That's important. If I had 0 on top and 0 on bottom, I could not make any claim as to what's happening. I need there to be something that's not 0 on bottom, and I have that, right? This is 0 over 3, if I simplify it. And 0 over 3 is 0. Yeah. Ian?
So why not just multiply by 1 over x to the fourth?
So if you multiply by 1 over x to the fourth, you'll get 0 in all 4 places.
Oh, because
And that's a problem, yeah. So that's a very good question. Why did we choose over x cubed? We chose over x cubed because it would leave the 3 as the constant piece that makes my denominator a constant when I'm done.
It's not like undefined or whatever.
Right, I don't want things to be undefined with the 0 in the denominator, exactly.
So if it is 0 over 0, you can't do it.
If it's 0 over 0, what it really means is that you made a mistake in what you multiplied by and you need to go back and take a look at it again. Yeah, it means it's undefined currently and you still can't make any claim as to what the answer is. Yeah. Okay, let's try another one. Now this looks a little bit different because I've got that radical. And there's workarounds for this. Even in algebra, there's a workaround that says, oh, it's kind of like. And it's one of those things that there's a workaround here too, but it's a more like proper workaround. It's not like waving my hands. In algebra, when we look at this, we kind of have to wave our hands and say, well, it's kind of like. I don't have to do that here. If I didn't have, so pretend for the moment, I'm going to scratch it out like it's not here. Pretend that piece wasn't there. I'll erase it in a second. Don't scratch it out on your paper. If you had the square root of x squared, what would that give you? That would give you x, right? You'd have an x on top and you'd have an x on bottom. Agreed? If I didn't have the scribbled out part, okay? So I really have exponents here that are the same. I don't really have an x squared on bottom because of the square root. These exponents are really the same, okay? So why can I scribble that out and I can say that? Well, because the scribbled out part is so much smaller because it doesn't have a power that's bigger than the x squared part that's already underneath the radical. It's just not big enough to affect things, right? It's kind of like saying, like, if I pick up that penny off the ground, it doesn't change my net worth. I mean, it does, but not enough to sort of matter, right? Like, it's inconsequential. It's very much the same thing with this little piece at the end. It's inconsequential to the actual process as you go to infinity, okay? So what we're going to do is we're going to recognize that this is really just x on top and x on bottom. Now, I still need to do what I did last time, which is to multiply by 1 over something. It's just that I'm only going to be multiplying by 1 over x. Now, the 1 over x on top, that's not a problem. X times 1 over x is 1, and we're all happy with that. But in the denominator, I have a radical piece, and I have a piece that's not, right? So I need to make amends for that, and how do I do that? Well, I'm going to write a separate step. You're welcome to write it within the same step, but I don't want you to look back at this later and say, where'd that come from? So I'm going to write out the same thing I have here, whoops, but I'm going to write it in a different form. So I'm multiplying by 1 over x on top, and I'm going to multiply by 1 over the square root of x squared. Okay, 1 over the square root of x squared is just x, yeah? The square root of x squared is just x. So I'm still just multiplying by 1 over x. I didn't change it, I just changed the way it looked. So on the bottom, let me move this down a little bit so it's a little easier to see. We have now, well, on the top we have 1. Whoops. Somehow I changed my color of my ink. That's not what I wanted to do. Okay. X goes to infinity. On the top I have a 1. On the bottom I have the square root now, and I'm going to push it under, and I'm going to do lots of steps. Again, you don't have to show all these steps once you have a feel for what's happening here. But I'm multiplying this out, and I'm multiplying, it's a minus, this out. This is what it looks like to distribute this, right? The 1 over x squared that's happening on the bottom, that x squared gets pulled underneath the square root. Okay? So it gets multiplied by the x squared that's there, and it gets multiplied by the x that's there. Is that okay with everybody? So as I simplify that, we have still 1 on the top. What happens to the first piece? What is the x squared times 1 over x squared?
1.
That one's 1. The second piece, what is x times 1 over x squared?
1 over x.
That's 1 over x minus. Okay, all good? This point right here is the same point that we get to here. I've got all the little pieces in a form that I can work with. They're either constants or they're a constant over x or power of x. They're constants. I have a 1, and I have this 1 over the x, okay? I do realize that there's a square root there. It doesn't affect anything in terms of how we process the problem. We're just going to take all the pieces. So this is the limit of 1 as x goes to infinity over the square root of the limit as x goes to infinity of 1 minus the limit as x goes to infinity of 1 over x. What is the limit as x goes to infinity of 1? 1. I still have my square root. What's the limit as x goes to infinity of 1 on bottom?
1.
That's another 1. And what's the limit as x goes to infinity of 1 over x? 0. And if it didn't turn out 0 here and something else, we could simplify it even now. But this is easy simplification, right? 1 minus 0 is
1.
1. And the square root of 1 is
1.
1. So I have a 1 on top and I have a 1 on bottom for a grand total of just the limit being 1. So could there be a coefficient? Like, could I have done all of this, but it didn't say x squared on bottom? It said 3x squared on bottom? Sure. Absolutely. Wouldn't have changed anything. Right? I would have ended up with a 3 underneath the radical here instead of a 1 right there. It would have changed my answer, but the process by which I was using to get the answer wouldn't have changed at all. Okay? One left. Trig. This one's different because trig does weird things. What do sine curves do? They bounce up and down, right? Sine curves bounce up and down, cosine curves as well. However, the top, sine, is bouncing up and down. What's the bottom doing? It's getting infinitely large. It's increasing, right? So if you have something that's bouncing up and down between 1 and negative 1, and you have the denominator that's getting increasingly large, so you're dividing by 100, you're dividing by 1,000, what's going to happen? Can you picture it? Your picture should be like sound waves, right? Sound waves as you get further away from the sound, right? If we're in this room, you're not hearing Dr. Tucker in the next room as loud as you're hearing me, right? Because it dampens as it goes further away. So you've got this dampening effect, and so you have something that's bouncing, but it's bouncing smaller. This is the image of what's happening. There is a bounce, but the bounce gets less and less over time. Does that feel like it makes sense? Okay, let's look at how we actually describe that then. Well, we're going to start with just the top for a moment. We just talked about the fact that the sine curve bounces up and down. Well, it bounces up and down between what?
1 minus 1.
1 and negative 1, right? Trig functions, yep, sine and cosine bounce between negative 1 and positive 1, and they keep going like that. So it's actually true that negative 1 is less than the sine of any angle, and so it might as well be sine of 2x, because that's our angle, and it's less than positive 1. Less than or equal to, so I should put, sorry. Okay, do you agree with that? Is that okay? All right. Now, as long as x is positive, which it is because it says x is going to infinity, right? X is positive. So as long as x is positive, I can take this statement and I can divide all 3 parts by x, and the inequality will stay the same. So I can write this as negative 1 over x is less than sine of 2x over x is less than or equal, they're less than or equal to 1 over x. And that works because x is positive. If this x were going to negative infinity, it would change the direction of my inequalities because I would be dividing by negative numbers. And I could ask you that. It's not an unreasonable question, but you have to recognize what x is really doing. Here, x is positive, direction stays the same. If x were negative, it would all switch. Okay? Now, that looks quite like the first one, does it not? I've just got my function now sandwiched in between 2 pieces. We're using what's called the sandwich theorem, or the squeeze theorem. Squeeze theorem is usually what it's called, but it's sandwiching, right? We're squeezing the result, because here's what we do next. We say, okie dokie. But what I really want is I want the limit of this thing in the middle, right? I don't really want just that piece in the middle, that function. I want the limit of it in the middle. So if I introduce the limit as x goes to infinity of the piece in the middle, what do you suppose I have to do to the outsides? The same thing. You got it. So on the left, I have the limit as x goes to infinity of negative 1 over x. And on the right, I have the limit as x goes to infinity of positive 1 over x. But what is the limit as x goes to infinity of negative 1 over x? 0. And what is the limit as x goes to infinity of 1 over x? 0. And what's squeezed or sandwiched in between? Well, the limit as x goes to infinity is what's in there. So the only thing that we are able to let that be then is 0, right? It has to be both bigger than or equal to 0 and smaller than or equal to 0, which means, well, it has to be 0. There's no other option that could happen here. So therefore, the limit as x goes to infinity of the sine of 2x over x is actually also equal to 0. It's clever, right? It takes trig and it turns it into the polynomial stuff that we were already doing. So every single problem that we're seeing in this section is going back to that theorem over here and getting it into a form of a constant over x. Doesn't matter what it looked like. We can change it into those pieces, and then we can apply this theorem. It's quite clever. It actually really is, because it means there's only one thing to do. It's just how do I get to that piece where it looks like this form? And you get there using algebra, or on the last one, using a little bit of trig knowledge with the limits of sine, right? Top and the bottom. Any questions? All right.